concentration of A and B begin to decrease more?
Is it because it's trying to regain its equilibrium?
It is. It is. But one of the major components about how we're going to, why that equilibrium needs to be regained is the fact that if we remove C, then C and D can't react because there's less C available. So the rate at which C and D go backwards then is going to be slowed down. Does that make sense?
Yeah, yeah.
Can you see why it's important to make sure we recognize that when a product is removed, it alters that reaction? A and B will continue to react because they're still around. But C and D's concentration, if C changes, decreases, then it can't react. Therefore, A and B will continue to react and the concentration of A will decrease. Okay? If at equilibrium concentration of A is 0.3 molar, all right, what happens if I add more D to this reaction? Camille, what do you think is going to happen if I add more D to this reaction? What's going to happen to the concentration of A? Yeah.
Okay, can you repeat the question? I'm sorry.
That's fine. If I have a concentration of 0.3 molar A at equilibrium, so everything's at equilibrium, but now I put into the mixture more D. How is the concentration of, how is increasing the concentration of D going to change the concentration of A if I, if it's at equilibrium and I add D?
The concentration will increase.
Concentration will increase. Why will the concentration of A increase if I put more D in?
Well, because you're adding more. It's the 8. It will shift to the left.
That's right, it shifts to the left. And the shift to the left, the simple explanation for why it shifts to the left, is because when there's more D around, it's easier for C and D to find each other, therefore the reaction rate increases. And the equilibrium shifts to the left. Okay, very good. Here's another scenario. Here's a chemical reaction, but let's say this reaction has a delta H of negative 100 kilojoules. All right. And if I take this reaction and cool it down, So if my reaction's at equilibrium and I cool down the reaction, all right, how will the concentration of A change? So if it's at 0.3 molar at equilibrium and then I cool it down, all right, let's see, Alyssa, any ideas?
If you cool the reaction down, will it make the molecules slow down so it will slow the rate of like the separate molecules finding each other?
Okay, that will happen on both sides, won't it? A and B will slow in which they find each other, but C and D will also slow, right? What we're looking for here is a recognition of what this means, this delta H minus 100. What kind of a reaction does it? Go ahead.
It's an exothermic reaction.
Exothermic. And we talked about last time that because it's exothermic, we could kind of write heat in here on this chemical reaction. Where would we write heat if it's an exothermic reaction?
Exothermic means it's releasing, so it would be on the product side.
That's right. So I'm going to write in here heat as if it's a product, because this is a negative sign, exothermic reaction. Now, once again, if these are my conditions at equilibrium, how will things change if I cool it down? Well, if I cool down this system, it's equivalent to removing heat. Now, apparently, to do the reverse reaction, C has to combine with D and consume heat. So if I have now removed heat and cooled it down, the reaction is going to be slowed going back towards the products. And by removing a product, the equilibrium will shift towards the product side. All right? Again, this told me that it was a exothermic reaction, therefore heat's over here, and if I say I'm cooling down the system, then that's removing heat, removing a product, the equilibrium will shift to the right. All right, Jace, here's one for you. C plus D going to E and F. Delta H equals 20 kilojoules per mole. All right. What will happen to the concentration of C in this reaction if I heat up this reaction? What will happen to the concentration of C if we're at equilibrium and I heat up this reaction? What will happen to the concentration of C?
Because it's positive, it's going to be endothermic, and then I think it's going to shift towards the left because it is towards the reactants because it is endothermic, and so the concentration of C should increase.
Okay, so what did we say we were going to do? Heat up this reaction, right? Is that what you heard, Jace?
Yeah.
Okay, so where should my heat go in my reaction if this is a positive 20 here? I'll emphasize that it's a positive. Where does the heat go?
I thought it would go towards the reactant because, is that right?
That is right. That is right. Because this is saying that this reaction requires heat to proceed. It consumes heat. Now, if I add heat to this system, that means heat it up, right? It's like I'm putting in more reactant. And so that will shift the reaction to the right, and it will decrease my concentrations of C and D. You see that, Jace?
Yeah. I think I just might have gotten a little confused. So, say it was like negative 20.
Uh-huh.
And it was exothermic, so that would make it exothermic. Would it push it towards the reactants then?
Okay, here's a situation. Delta H, some negative value. I'll put a number in there so it kind of looks like something more familiar. Okay, and now what did you say we're going to do? Heat it up or cool it down? What did you say?
Well, so we're like, I guess because it's negative, it's going to be cooling down because we're losing that heat. So the heat's going to be at, like, you're going to add the sign to the product.
Well, when we ask these types of questions, the reaction is at equilibrium. The reaction is at equilibrium. So the reaction is just sitting there in a container. It's not heating up or cooling down. It's at one temperature right now. Right? We've already reached equilibrium. And now the question is, how will the equilibrium shift when we change the temperature? So what kind of temperature change should we make, Jace? We're going to stick our container in ice, or we're going to stick it in an oven and heat it up?
Let's say we put it in ice.
Okay, so if we cool down this reaction, lower its temperature, how will the reaction shift? How will the equilibrium shift? Will it shift to the right or to the left? What do you think, Jace? Where does the heat go, first of all, in our reaction based on that information?
The heat goes on the right side.
Very good. So the heat goes over here. So now cooling it down is equivalent to doing what in terms of the heat, Jace?
Reducing it, so that would cause it to go towards the reactant.
Go towards the products over here, right? I'm removing this. So,
Oh, okay.
so
Yeah, that makes sense. I was a little confused, but
Yeah.
since you're removing that, you have less of it on the right, so that's why it's going to be pushed towards the right.
yes. If there isn't any heat, this reaction can't go to the left very good, right? This reaction goes to the right all the time, regardless of whether there's heat or not, and it will be producing more heat. Okay. I think we have created a decent review video for all sorts of things that we've already gone over. Oh, I guess there's one more thing that we could talk about. All right. So here we go. A plus B going to C plus D. K for this reaction equals 0.047. That's the K for this reaction. What does that 0.047 mean for us, Sarah? How is that 0.047? Am I supposed to be able to know something simply by looking at that number, Sarah?
So that could tell us that the concentration of the reactants is larger than the concentration of the products.
Very good. And if you don't, understand that, then just practice writing your equilibrium statement and then looking at what that means in terms of this quotient here, right? So we're saying that because this is less than 1, the product of the reactants is higher than the product of the products. So that means at equilibrium, there's more of A and B. And we could tell that because this K value was less than 1. So as the value for the equilibrium constant gets more than 1, it tells us that there's more products at equilibrium than there are reactants. Okay. Well, I guess I didn't need to erase that. But that's information to know. Now we're going to hijack the rest of this information and tell or answer this kind of a question. So if at equilibrium, the concentrations of A, B, C, and D are 0.2, concentration of A, 0.3, 0.04, and and D is unknown. D is unknown. So the concentration of A, concentration of B, concentration of C. Can I identify what the concentration of D will be at equilibrium? Can I identify what the concentration of D will be at equilibrium? Any ideas, Camille? How would I do this?
I don't know. This is hard.
So this is the unknown. This is the unknown, the concentration of D at equilibrium. I shouldn't have erased that out. We'll rewrite it now. We know that 0.047 equals the concentration of C times the concentration of D over the concentration of A times the concentration of B, right? So I can use the concentration of C here, 0.04. What's that? Yeah, I can just put them all in, right? Does that make sense, Camille?
Yes.
So why don't we get a calculator and see what this value is?
I'm doing it.
Okay.
And then. Okay, wait. So I did 0.04 divided by 0.2 times 0.3, and then I divide that by 0.047, right? Is the answer 14.18?
I don't know exactly what you did there, but all you have to do is 0.047 divide by 0.2. No, sorry, times by 0.2. Get it over here. Times by 0.3. Get over here, and then divide by 0.04. And the answer is 0.0705. Okay? All right, so what is this basically telling us? It's telling us that if we have the K and we have concentrations of reactants and products of all the different species at equilibrium, except for one, we can identify it. All right? Okay, another little review here. Chemical reaction, A, B, C, D. All right. I can identify what the K is. If I'm not given the K, I can identify the K if I'm given these concentrations at equilibrium. All right. Alyssa, you want to solve that one for us really quick? What is K? So while she's doing that, I'll remind us that we know that K will equal the concentrations of the products over the concentrations of the reactants, and the concentration of C is 0.03, D 0.02, A 0.1, B 0.2.
I got 0.03.
All right, there's our K for that reaction. Okay? Excellent. Now, I've been lazy and we haven't used any other coefficients than 1 on most of these problems. But remember, if whatever these values are, the coefficients, they're going to have to be raised to those values here. Okay. So, one last review that we'll do is the problem that we did before we left last class, which is this one right here. Okay, again, this is a review. We just did this last class. Here's a chemical reaction. K equals 10,000. What are the equilibrium concentrations if we're provided starting concentrations? Okay, so again, this is something new. Here, we're given the equilibrium constant and all of the concentrations, but not the concentrations at equilibrium. We're given the initial concentrations. And we want to know how the reaction concentrations will shift to reach equilibrium. And once they reach equilibrium, we want to know the concentrations of all the different reactants and products at equilibrium. Okay? Now, let's see. Sarah? Let's see. Whose turn was it? Was it Jace? Did you get to watch last class? Do you know how to approach this to start off with? Or maybe you remember from other classes.
No, yeah, I was here for the last class.
Okay. So, I mean, it was kind of near the end there, so I wouldn't be surprised if you didn't remember. Do you remember anything about how we approach this?
Yeah. Well, we're trying to see if it's at equilibrium.
Okay, that's right. First, we have to check whether it's at equilibrium, right?
Yeah, so we have to set up the equation, so it's going to be d squared over a times b.
Okay.
And then it gives us the concentrations, obviously, so it's going to be 5 squared divided by 4. And then once we solve for that, it's going to be 25 divided by 4, so 6.25. And so the equilibrium constant is 10,000, so we're way below that. So I think it started to move in the direction of equilibrium, but we're not anywhere near equilibrium.
So which way does this reaction have to shift to get closer to a K value of 10,000?
It has to continue to shift towards the products.
That's right. It has to shift towards the products. Very good. So we identified what we call the Q, the current quotient, right? And that was 6.25 by writing the equilibrium expression, putting in the values they provided for us, and we found that we're not at equilibrium, but we can reach equilibrium if we shift towards the product side. Very good. Sarah, do you remember what the next step is?
So I think we could start writing stuff out like in a line. So if we start with the initial values,
Okay.
we have
Very good. So we make, what did I call this? Do you remember?
I'm not sure if you called this, but is it like an ice table?
It's right. It's not an ice table. Well, you can use the word ice table, but then it doesn't reminisce ideas of going to the beach with a lot of soda in a container, right? So this is called an ice box. Very good. You could call it an ice table too, but very good. So what does the I stand for in ice table?
Initial.
Initial. So we want to kind of have our chemical reaction up above here. All right. So A's initial concentration is 0.2. B's initial concentration is 0.2. Oh no, not 0.2. 2, right? And D's initial concentration is what? 5. What do we do next, Sarah?
All right, so now we have the changes. Or I'm not sure what C stands for, but
C stands for change. That's right.
okay. So I think A is going to be, so we're going to be losing A since it's moving to the product side. So it's going to be minus X, I think.
Mm-hmm. Very good.
Okay. And B is also minus X.
Uh-huh.
And then D is plus 2X.
Plus 2x. Why did we put 2x here?
Because of the coefficient on the original equation.
Okay. Very good. Now, after we have the initial and the change, then the equilibrium concentration is just the sum of those two. So this is going to be 2 minus x. This is going to be 2 minus x. This is going to be 5 plus 2x. And these are our concentrations of our solutions once we've reached equilibrium. All right? So the equilibrium expression for this, again, is d squared over concentration of A, concentration of B. I should say not just d squared, but the concentration of d squared, right? Times the concentration of A over the concentration of B at equilibrium. And again, those values are going to equal our K, which is 10,000. Okay, so equilibrium concentration of D, that's this, 5 plus 2x. So I go 5 plus 2x, that quantity squared. And then down here, 2 minus x times 2 minus x. All right, and again, this value equals 10,000. So this can be simplified for this scenario. 5 plus 2x squared over 2 minus x squared. 2 minus x times 2 minus x is 2 minus x squared. And that is going to be equal to our 10,000 again, right? This 5 plus 2x squared over 2 minus x squared can be thought of this whole quantity squared. And what that does for us is then...
Minus X.
Go ahead, what's that?
Can you explain why it's 2 minus X?
Why the equilibrium concentration is 2 minus x in this spot right here?
Oh, that's just the equilibrium.
Yeah, so this is the concentration of A, so I wrote in there at equilibrium, right? So I use the equilibrium concentration of A and put it in there. Okay, good. So we got 5 plus 2x over 2 minus x, the whole quantity squared. So then I can take the square root of these sides and get 100 being equal to 5 plus 2x over 2 minus x. And then I can continue, multiply this side by 2. 200 minus 100x equals 5 plus 2x. And then I can just collect like terms and finish that problem. And the x value ends up being 1.91. 1.91. So, let's see. Jace, what does that 1.91 equal to? What does that mean?
That's just equals to x, so we're gonna have to put that. We're gonna have to put it into each, like where it says E on the board. We're gonna have to put that 191 into like 2 minus 1.91, 2 minus that, and then 5 plus 2.1
That's right. Very good. Very good. So that's just our shift. And so the concentration of A and B would be solved by putting X into here. And the concentration of D would be solved by putting X into there. All right. So all of that is review.